everyone, welcome back to Orillusion. Here is WebGPU basic tutorial. Last time we introduced some basic concepts of spatial transformation. One is the modal transformation, which is translation, rotation, and scaling. The other one is projection transformation, including the perspective view and orthogonal view. And today we are going to implement it. We'll draw a 3D cube with the fixed viewing point and let the cube rotate automatically around its center. We'll continue to work on the demo code from the last tutorial, the color triangle. Let's first review some points from the last tutorial. And we firstly need to establish a virtual world coordinate system. It doesn't have to match the coordinates of the clip space or NDC. And then we can build the vertex information for this model centered on the origin of this coordinate system. We pass the vertex information through the vertex buffer into the vertex shader. We also need another MVP matrix of the same coordinate system, including both modal transformation and the projection transformation. We'll write it into a separate GPU buffer and then insert it into the vertex shader via the bind group. And then in the vertex shader, we multiply the vertex data with the MVP matrix. Today, we'll take this coordinate system as an example to build a cube with the length of 2. People may be familiar with the WebGL default coordinate system. And also many math libraries also use this coordinate system by default. So we directly add more vertex coordinates and under this coordinate system. A cube has 6 faces and a face contains at least 2 triangles. If we don't use the strip mode, that one triangle needs at least 3 points. So one cube needs at least 36 coordinates information. If you are interested, you can mark these 36 points according to the coordinate system in this figure. If without any more matrix transformation and output this set of vertex coordinates, let's think about what kind of graphic we'll get. Okay, we see yellow fulfill the screen. And why is that? Because we directly output according to the range of NDC. So the cube will occupy the NDC space. And half of the cube was cropped because the z was less than 0. So what we get is actually the projection on the plane where z is 1. So how can we get a cube with a normal viewpoint? Now let's deal with the matrix transformation. We can keep the old pipeline configuration, including the vertex buffer and color buffer. But we need to create another GPU buffer to store our MVP matrix. Here we declare it as MVP matrix and create it through device create buffer. As we said in the last tutorial, the 3-dimension transformation needs a 4x4 matrix. And the matrices can be decimals, so we have the 16 float 32. And accordingly, we can add another entry here because color has already used binding 0 position. So here we can use the position of binding 1 to pass in the MVP matrix. And of course, you can change the position of these two. It's just like what we did in the previous fragment shader, to use the group 0 binding 1 to get the MVP matrix. Just it is a MIT 4x4 format, not a VEC4 anymore. This matrix type is defined by WGSL. Then we can use this MVP matrix in the main function. We multiply by the coordinates of the input vertex position. GPU has optimized for this matrix calculation, so we don't have to implement the multiplication algorithm ourselves, and it is much faster than the calculation in JavaScript. But we need to pay attention here. The vertex coordinates we pass in is always 1×3 array, and it can't be directly multiplied by a 4×4 matrix. So we need to turn it into homogeneous coordinates as we discussed last tutorial. We can change original data before passing to the vertex shader, but an easier way is to write vec4 directly here. And the vertex shader will help us to automatically fill one position to compose a vec4. Another thing we need to pay attention is the order. It must be MVP matrix times position. You cannot swap them. This is some transformation of matrix calculation. We are not going to introduce this in detail here. We just need to remember the order of this multiplication. Okay, let's save it and take a look. There is an error here because we forgot to change it into binding 1. Alright, let's save it and try again. Okay, there is no graphics displayed now because data in the MVP matrix is empty, i.e. it's all zeros. So the matrix multiplication result is all zeros. And if you convert it into NDC coordinates, it's equivalent a point at the infinite. So now let's change the MVP matrix. Let's review how to generate a MVP matrix. But here, let's return the MVP matrix first. For developers, we don't need to hard write in those various matrices. We'll use some math library such as GL matrix as a matrix calculation library. So under this directory, we can install the GL matrix library through npm. Tap npm install gl-matrix. And then we can import it into our TS code. And we'll use math4 and vec3 here. So we can just import these two modules. The API is very easy to use, and let's firstly look into the math4. You can generate a 4×4 matrix through API math4.create. And this will be our model view matrix to store the result of the model transformation. As we know that there are 3 basic model transformation: translation, rotation, and scaling. So how to implement those? For example, we want to translate the model. Then we can use math4 translate API. We need 3 parameters here. The first one is the target matrix to store the result of matrix transformation. The second is the original matrix that need to be translated. And the third parameter is the vector of translation. We set the first 2 parameters as a model view matrix. And then we create a vec3 from values API we just imported, which means the matrix will be translated into this direction. Similarly, scaling transformation also has these 3 corresponding parameters. We can use this math4 scale API. And also, the result will be written into the model view matrix. But rotation is a little bit more complicated because the calculation method around 3 axes, x, y, z, is different. A general method is to make 3 rotations based on 3 axes individually. So we have 3 APIs: rotate x, rotate y, and rotate z. And the parameter structure is the same as before. But the third value is the number of radians rotated according to the axis. So with this helpful APIs, we can easily perform the spatial transformation on this model. Any model transformation can be regarded as the translation, rotation, and scaling from the arrangement. So given the parameters of the model, then it can get the result of the final model view matrix. So let's look into our original cube model. We can still abstract the three parameters for translation, rotation, and scaling. The initial states for this cube, the translation is 0, 0, 0, rotation is 0, 0, 0, 2, and the scaling is 1, 1, 1. So we can change the value in these transformation vectors to achieve a model view matrix. So we need to generate a projection matrix. And in this demo, we consider the situation that the camera will not move. So we'll take this structure in this diagram. The camera will be positioned at the original point and facing the negative z-axis direction. So now let's initiate a matrix for the projection matrix through the API made for perspective to create a projection matrix that matches the perspective view. And the first parameter is where the created matrix will be stored. That is the projection matrix we created, obviously. And the second parameter is the viewing angle size. That is the angle of this first term. You could set it according to the scene, but generally we'll use 45 degrees and 30 degrees to simulate the human vision. And note that this is a radian value, so we set it as pi over 2. Next one is the viewing angle ratio, which is the ratio of the width and height in the near and far planes. In order to maintain the normal display ratio, we generally use the screen space as a reference. That is also the aspect ratio of our canvas. And the last two parameters, we need to specify the distance between the near plane and the far plane, which is the depth of our scene. And the near plane can't be 0 because we can't projection on the 0. So let's set it as 1 here. There's no too much restrictions on the far plane, but it of course should be greater than the distance of the near plane. Let's set it as 100 here. Now we have a perspective projection matrix. And now let's go back to the standard coordinates of the clip space. With the model view matrix and the projection matrix, we can use the mat4 multiply to multiply these two matrices together. And then we can get a MVP matrix. In this API, we also need 3 parameters. The first one is where the result will be stored. And the next two are which two matrices will be multiplied. So let's generate a new MVP matrix and then multiply the projection matrix and the model view matrix. And let's pay attention to the order here. In the model view transformation, we do the translation first and then rotate and then scaling. And in the MVP matrix multiplication, we multiply the projection matrix by the model view matrix, and this order cannot be changed either. And this is actually some mathematical related information, and people who are interested in could research afterwards. We're not going to introduce in detail here. And finally, the calculation in the shader is MVP times the coordinates, and this order cannot be changed either. So please remember these 3 orders. And finally, we can put MVP matrix to the MVP buffer in the pipeline, and we can call device QRED buffer here. The default type of MVP matrix is MIT, but actually it is a float 32 array. So we need a casting here. Okay, let's save it and see the effect. It is empty, and why is that? Let's look into the set diagram of the current space. Our camera is located at origin, and our cube is at origin too. As we just said, the distance of the near plane in the frustum is 1, so the entire cube is just outside our frustum. We can change the near plane distance smaller, let's say 0.1, and we get a full screen yellow. And let's go back and to take this diagram. Because the near plane is very close, so part of the cube occupies the full frustum space. So we get a face of the cube from the projection. What if we would like to see a full cube? If we don't move the camera, then we can move the cube. For example, let's move the position of the cube into the negative directory of the z-axis to keep it away from the camera. So the cube can be wrapped by the virtual frustum. Let's change the value of z into -2. It seems not far enough. Let's try -4. Okay, now we can get the full cube. And we can see here, if the value is smaller, then the rectangular area will be smaller. Even though we didn't change the size of the original cube data. That is because the perspective projection space. So the model will be automatically scaled according to the distance. We can also change the rotation and the scaling here. Let's say rotate 0.5 on the x-axis and save it. Let's see. Okay, we can see that the box has been rotated somehow. But the uniform color is not very easy for us to see the difference. Now let's change the fragment shader to make it easier. We have introduced before, in the vertex buffer, we can customize the returned structure in the vertex shader. Apart from the default built-in position, we can also add some other data. For example, our position at location 0. We add a frag position, and the return value of the main is changed to return this structure. We declare a variable named out, and we can just let out position equals to MVP multiplied by position, and make the out.frag position equals position. So we can return the original position information before the multiplication. And then finally, we can return the out variable. As we did in the last tutorial, in the fragment shader, we can get a location 0 frag position variable. And we can use this variable as directly as the color information. Because our pipeline has already imported color, so in WGSL, we must declare the group. Otherwise, it will report error. And here we just simply call color. And let's save it and see the result. Okay, we see that the box becomes a RGB transition color. Let's briefly explain this. And previously, we just know that the vertex shader will pass the data to the fragment shader, but we didn't explain in detail. But let's think about it, how the vertex shader and the fragment shader works. Let's take a triangle as example. So the vertex shader will return a 3 vertices. And the fragment shader will frame this as a triangle face. Then how to deal with the data in the middle? GPU will do the interpolation method to process the data according to each fragment source, which is 3 data. And it is a linear interpolation. Each point we see here is actually a pixel or a fragment that returned by the fragment shader. And the range is also from -1 to 1. So if we use the frag position as the color, then we will get a transition color interval. But because many values are less than 0, so we get a large black area. So we need to modify the frag position here. Let's add a vec by 1, 1, 1, 1 to make the range from 0 to 2. And then we multiply the result by 0.5 to make the range located in 0 to 1. Okay, let's save it and see. Okay, the color is much more brighter. There is no black area. But we can discover a new problem. And why this small triangle cover part of the large triangle in the front? Because even though we set the projection matrix to make the coordinates of each point to align with the perspective effect, but for the space NDC, we just projection all the points into z equals to 0. So it cannot distinguish the side which is in the front and at the back. The depths only affect the drawing order. The smaller face which is far away will be displayed before the larger face. To solve these problems, we can manually optimize the drawing order of the triangle surface, but it is not efficient. It will be difficult for us to do the real-time sorting in the complex scenes and models. So in modern graphics, we'll use the depth test to solve this problem. Depth testing is part of the rendering pipeline, and it is not enabled by default. And if it is enabled, it will compare the depth of each fragment before passing into the fragment shader. If there are occluding fragment, then the fragment has the more depth, which is away from the camera, will be discarded. In this way, to make sure that the surface in the front will be drawn. Okay, let's enable the depth testing. And the GPU will compile the depth information of each fragment in the same position. In modern graphics, we generally use textures to store the depth data. So we also need to set the data format for the depth map. This format mainly refers to the precision of the depths. And here we use the basic 24-bit depth map. We'll explain this in detail later. And we also need to create a depth map. Just copy the code directly here. And we'll cover this in detail in the future tutorial. And the size of the depth map must be matched with the size of the canvas. And we pass the size into the init pipeline. And we add the type for the size. It is an object that contains 2 numbers. And we pass the depth map out like the other variables. And then in the draw function, we can use this to configure the render path as the color attachments. So before each drawing, we need to tell the path how to process the canvas information. Where is the target? And if we clear the canvas before drawing, and what color used for clearing. And it is same for the depth information. We also need to tell the path to how to deal with the depth information and on which texture do you need to clear the original content before drawing, and also the clear range. Because the value of the range of z-axis is 0 to 1, so 1 means completely empty. Okay, now we can get a good result. The smaller triangle has been discarded, code is behind. It is discarded by the GPU and saved the workload of GPU rendering. It is also good for the high performance. Here is an error because the pipeline object has not been defined the tab. Okay, let's edit. Now there is no error. Okay, to double check if the rendering effect is correct, let's make it rotate. And let's briefly introduce the animation principle. And no matter it is 2D or 3D, it is essentially just a repetition of drawing. If the change is small and the frequency is high, then we can't tell the difference by the human eyes. It's just like a continuous animation. Normally, we'll implement a animation loop to continuously changing the parameters of the objects in the scene, continuously override the previous frame. So what should we do to implement a loop drawing method? For example, we can use the setInterval function to call the draw function periodically. For example, we run this every second. So in this way, when we make the color change or position change, the view will not be updated right away instead of just after 1 second as we said here. But if the interval is very small, let's say 20 milliseconds, this will make the change very smooth. Generally speaking, if the interval is less than 40 milliseconds, which is more than 24 frames per second, then it's gonna be an animation for the human eyes. So let's change this into 20 milliseconds. And then make a change on rotation on X and Y axis on the same time. We also need to update the entire MVP matrix every time. So we put this part of the code into the loop, and it will be updated every 20 milliseconds. Okay, let's see the results. Now we can see it is rotating continuously, and we can see the entire 3D perspective view. And we need to know here, the animation interval cannot be infinitely smaller, and not even the smaller the better. For example, we can set it as 10 milliseconds, but we don't recommend to do so. Because whether CPU or GPU, they will take some time to execute the code and process data. So the interval cannot be infinitely small. For larger scenes, it will take more time to execute. 10 milliseconds is not going to be enough for the calculation. And also, the callback of setInterval and set timeout will be delayed. It will also affect the other asynchronous effects in the browser. Secondly, our monitors have inherent refresh rate. In general, it is 60 Hz. That is equivalent to 16.6 milliseconds. So although your refresh interval is less than 16.6 milliseconds, and your result won't be shown right away. And besides, human eyes cannot tell the difference. And instantly, it will waste the performance of CPU and GPU, so the refresh rate of the device cannot be aligned. It will cause some missed frames and wrong frames. Especially in the web environment, JavaScript has no ability to control the underlying refresh rate. The browsers work according to its own interval refresh mechanism. So if the animation rate exceeds its refresh rate, it doesn't make any sense. Generally, in the web development, we use the API called request animation frame. It means to make the callback every time the browser refresh. So we put the above code into a function called frame, and then we pass the frame into request animation frame API. And in the frame function, we can call request animation frame again to start an animation loop. And its calling frequency is depending on the refresh rate of the device. If the main thread of the page is busy before the next refresh, or the GPU cannot handle that, and this callback function will be automatically postponed to the next frame. Also, if the page is in the background or the browser is in the background, then this loop will be also automatically suspended. So we generally recommend to use this API to do the animation processing in the web. Okay, back to the cube. We can see that the whole view is 3D perspective. But if we turn off the depth testing, let's take a look at the effect. And of course, we will find this occlusion error, But we just introduce another knowledge point here. With the depth testing off, we can see the behind faces. It is actually the inside of the cube. As we know that every coin has two sides, for an enclosed cube, we shouldn't see the inside. So how can we discard the inside faces? We can set in the primitive to enable the graphic cooling. And it is not enabled by default, so we can set cool mode as back here, which means the interior of the box will be not rendered. Okay, we see the result. It looks like the effect of turning on the depth test, but actually the principle is different. Depth testing is to discard the covered surface at behind, but cooling mode is just to use the 3D closed structure of the cube to remove the back of the interior. But if it is a expanded figure or a separate face, then the effect of the deep testing and the cooling mode is different. Okay, that's pretty much for today. It's a lot to digest. Please download the code from our GitHub repo and practice after this. You will use the 3D transformation and learn how to draw multiple objects. Particularly, we'll learn several ways to switch data pipelines. Alright, that's all for today. Thanks for watching. Welcome to subscribe and leave any questions. I'll see you in the next video.